In this lesson, we'll consider some prominent organic reaction mechanisms that show us some good examples of how these reaction steps that we covered in the last lesson might show up in a more extensive complex reaction. Our learning goals will be to learn the distinction between stepwise and concerted reactions, and then we'll take a little bit deeper look at the hydrolysis reaction and consider some of the ways that it's very important in our own biochemistry. I'm going to start by talking about substitution reactions. This is actually, on the face of it, a fairly simple type reaction where we have an anion. I've written this in red at top as Y minus, adding to an alkyl X, Rx, to form Ry and an X minus ion. So in a sense, what's happened here is that the Y anion has replaced X in its attachment to the alkyl group R. All right, so a direct substitution where we've substituted Y for X. Now I want to show you a couple of examples of this reaction involving bromides, alkyl bromides, and we'll see some of the varieties of outcomes that we can get from these reactions. Okay, in the first case, we're going to take hydroxide ion and react it with 2-bromobutane, and we get 2-butanol from that, so the hydroxide now appears where the bromine was, and a bromide ion as the result. Now if we do some experiments on this reaction and characterize its reaction rate, we would get a rate law that looks like the one shown at right. Namely that the rate is equal to a rate constant times the concentration of hydroxide ions times the concentration of the 2-bromobutane. All right, so in a sense we'll consider this to be a bimolecular reaction because the reaction rate depends on both the two reactants in an equal fashion. All right, this won't always be true. But in this bimolecular reaction, it basically is saying that the initial step of the collision between the two reaction partners is the one that determines the overall rate of the reaction. That's the clue that we can take from this. Now we're going to contrast this with a slightly different reaction where we're going to react cyanide ion with T-butyl bromide. Okay, so again we're looking at an alkyl bromide, a little bit different alkyl bromide, but we're seeing how it reacts with a known nucleophile, a negatively charged anion that has lone pairs of electrons that are non-bonding. Now again we'll see that the cyanide replaces the bromine on the T-butyl bromide and forms T-butyl cyanide and again gives a bromide ion. So in some ways this is very much like the previous reaction. The cyanide has directly replaced the bromine in the alkyl bromide. But in this case, when we do an analysis of the rate law, we find that it's only dependent upon the T-butyl bromide. So in other words, it has sort of a unimolecular aspect to it. It only depends on the concentration of one of the reactant molecules. So what's going on here? Why are these two giving rise to different rate behaviors? As we've already seen, the reaction rate is intimately related in many ways to the reaction mechanism. So there's something about these different reaction rates that's telling us that these two reactions proceed by different mechanisms. But the question is why? Why would these be different mechanisms? Well, we're going to look at a few clues to see if we can sort this out. The first clue is that all substitution reactions of this type, where we're substituting one thing for another on a carbon atom, they all follow one of these two rate laws. They're either the first one bimolecular or the second one unimolecular. So these mechanisms, whatever they are, appear to be universal for substitution reactions. The second clue is that if we just look at the bimolecular substitutions, so that's the first case, involving a single enantiomer, they produce only a single enantiomer. And if they're racemic, that is, they have both enantiomers present in the mixture, then the product mixture is also racemic, so we would get both enantiomers. So that's presuming that the carbon at which the substitution is happening is a chiral center. Okay, so I should clarify that. Now what happens in unimolecular reactions? So that's the second case. They, no matter what you start with, they always produce a racemic, that is a 50-50 mixture of the two possible enantiomers. Again, supposing that the carbon at which substitution occurs is a chiral center. Our third clue. The enantiomers that result from a bimolecular rate process always have the inverse geometry from the one they started with. So in other words, it inverts the stereochemistry at the chiral center. So that's a really interesting clue, and it's going to tell us something very direct about the mechanism of these reactions. So let's look at that first case, the bimolecular case. So we see the hydroxide ion coming in. It is a nucleophilic attack. The hydroxide ion is a good nucleophile. It's got a pair of non-bonding electrons and a negative charge. And it's going to attack the electrophilic center, which is the carbon atom on the 2-bromobutane. All right, when this happens, in effect, the molecule enters into a transition state. Now, I also want to point out that the hydroxide is approaching the carbon from the side opposite where the bromine is. So when it forms this transition state, we actually have the hydroxide on one side and the bromine on the other. And both of them are in a weakly bonded state with the carbon atom in the middle. And so one can think of what's happening here is that the hydroxide carbon bond is beginning to form and the carbon bromine bond is beginning to break. All right, when we carry this on through, the hydroxide carbon bond has formed, the bromide has broken off, and in effect what has happened is it has inverted the other three things that are attached to the carbon. So it has, in some sense, flipped the carbon over. And this can help explain why we see an inversion of that chiral center. If the carbon is chiral, which it is in this case, we would start perhaps with one stereoisomer and end with a stereoisomer of the opposite sense once it has gone through this substitution reaction. All right, now as for the label, and you see the label in the title of the slide, we call these SN2 reactions, and that label actually stands for something. The S stands for substitution. It's a substitution reaction. The N for nucleophilic. This is a nucleophilic attack on a compound, a bromine compound. And it is a bimolecular reaction mechanism. That is to say, the rate law is a bimolecular rate law. So this, when we see a SN2, we need to process all of those things. Now, the thing that's a little bit confusing here is it may be a bimolecular reaction, but it happens in one step. So one step direct from reactants to products. Now, we can draw this in a reaction energy diagram, and it looks something like this, where we start with reactants, which are the hydroxide ion and the 2-bromobutane, and we go over a single transition state. The thing that we've drawn in the middle there is the transition state. And then we go down to products. So it's a very smooth process. It happens continuously, and for this reason we call this a concerted reaction. So we see that everything happens more or less in a clean, single continuous reaction. And this is going to be different from what we'll see in the other case. So let's take a look at that. So here is the other possibility. This is the reaction of cyanide with the T-butyl bromide. And now I show the T-butyl bromide first because in the first step what happens is that we have loss of a leaving group. The bromine breaks off from the T-butyl bromide. So that's step one. What it leaves then is a carbocation intermediate, and that carbocation is a tertiary carbocation. So remember, when we talked about carbocations in the last lecture, tertiary is the most stable, and secondary, then primary, are less stable than the tertiary carbocations. Well, it turns out that this is like a trigonal planar cation, okay, because there are only three electron groups attached to that carbon atom. It forms a trigonal planar structure, so it's flat. Since it's flat, that cyanide nucleophile, so now the nucleophilic attack is going to happen, but it can equally well access the carbon atom from either side. So instead of inverting the stereochemistry at the carbon atom, it now can actually form both possible stereoisomers. So it attaches at either side. And so we see the products are a mixture of the two possibilities, that it could either invert the geometry of the original bromide or have the same geometry of the original bromide. In this case, we call these SN1 reactions, as the S and the N both still stand for substitution and nucleophilic, but now the 1 stands for unimolecular. I'll note also that there are elimination reactions that also show similar characteristics to these two substitution reaction mechanisms, and those are called E1 and E2. Now the reaction energy diagram for this one is going to show a little valley where that carbocation intermediate exists. That's always going to happen when you have an intermediate that has some stability, which this one does. So the slow step is going to be the loss of a leaving group, loss of the bromide from the T-butyl bromide. And then the second step, which is going to be the carbocation reacting with the cyanide ion, is going to be a relatively quick step and is going to lead to products. So what I want you to be able to do is to tell the difference between the reaction energy diagrams for SN1 and SN2. I mentioned in the SN2 that it was a one-step reaction even though it involved a bimolecular rate law. We have exactly the opposite in SN1. It is a unimolecular rate law because it depends only on the first step, which is only dependent on the T-butyl bromide, but it is a two-step reaction. And so for this reason, we call these stepwise processes in organic chemistry. So the opposite of concerted is stepwise. Let's talk a little bit about hydrolysis reactions. Now I'll remind you that a hydrolysis reaction is a double displacement, and basically what happens is water enters and it breaks a bond, and also water falls apart. So it forms two new molecules. It's a double displacement. So in this case, for example, in abstract sense, H2O would go in to break an AB bond, and part of the H2O would attach to A and the other part would attach to B. So in this case I've shown A attaching to the OH part and B attaching to the hydrogen part. Now this is important because it's how we can convert acid derivatives to their parent acids. And this is going to call on your memory a little bit, but when we talked about the carboxylic acids and acid derivatives in the last class, in the last course, we indicated that acid derivatives were related to the parent acid through this hydrolysis mechanism. So if I have an acid derivative that is shown at the far left there, and it reacts with water, it's going to produce an acid, and it's going to produce a hydrogenated derivative, or HX. And that X depends on what kind of acid derivative it is. If the derivative is an alkoxy group, it would be an ester. If it's an amine group, it would be an amide. If it's a chlorine, it would be an acyl chloride. And if it's a little bit more complicated thing, it would be an acid anhydride. All right, so it doesn't matter which of those it is. We have these hydrolysis reactions available where water can come in, break that bond, and reform the carboxylic acid and the other group with it. Okay, so what about dehydration? Dehydration is also a double displacement reaction, but it's a double displacement that forms a new bond to a carbonyl group, and it produces water as a product. Now, I want you to look closely at the reaction at the bottom there, where we have a carboxylic acid reacting with an amine to produce an amide and water. Well, essentially, that is the opposite of the hydrolysis reaction. In fact, if we reversed it, it would be a hydrolysis reaction. It's the reverse of hydrolysis. But this is the process that amino acids use to form polypeptide chains. So this reaction that we've just shown is in effect what happens when we begin to make proteins in our cells. Now let's focus on esters and the hydrolysis that they can undergo. So I've drawn basically an abstract ester is R-COOR prime, and R and R prime can be different alkyl groups, but the one that I've shown below that is methyl acetate, where both R and R prime are given by methyl groups. So when that undergoes hydrolysis, theoretically, it would form acetic acid, so the OH is attached to the carbonyl group, and it would form methanol, where the H is attached to the CH3O group. All right, so the elements of water are shown in blue, both on the reactant side and the product side. So this would be ideally what happens in the ester hydrolysis of methyl acetate. But it turns out that esters do not participate in hydrolysis very readily. In fact, it takes them a long time and it requires assistance. It needs a catalyst or an enzyme to help ester hydrolysis happen. Now, why might this be important? Well, let me show you an example where ester hydrolysis comes into play. Triglycerides are the way that we store fats in our bodies. And basically, a triglyceride is shown there on the lower left, and it's composed of a couple of different parts. Let me spell those out a little at some detail. So the core of a triglyceride is the 3-carbon chain that's shown at the bottom of that molecule on the lower left. Those 3 carbons are attached to each other, but each carbon is also attached to an oxygen, and each oxygen is attached to a carbonyl group. So in effect, what we have there is a triester. Okay, each carbonyl is the carbonyl for an ester part, and they all hook up to that same 3-carbon group. Now at the other end of the ester group, I've drawn R as the group. Well, those R's are long chain hydrocarbons, and in fact those long chain hydrocarbons are what makes up essentially the essence of a lipid. So those are basically coming from fats. So this triglyceride is basically a composition that has 3 fats attached to a 3-carbon chain. Now, when it undergoes hydrolysis, and I've shown three waters there that would be attacking the 3 ester CO bonds, that's where they would break the molecule. So in essence, what happens at the end of hydrolysis is it would form glycerol, where each of the oxygens attached to the 3-carbon chain would now be attached to a new hydrogen that came from a water molecule, and the 3 carbonyl groups would now be attached to OHs. They would form carboxylic acids, and the other end of that carboxylic acid would be that long chain hydrocarbon that I'm calling R. So this, in essence, is how our body takes fats from an animal source, which would be in the form of a triglyceride, and breaks it down into fatty acids so that we can use that to generate energy for, for whatever our biological needs are. So very important process. But the key here is that this process cannot happen very readily unless it has enzyme assistance to help it out. All right, now another way that ester hydrolysis can occur is through a process called base-promoted hydrolysis. Let's go through that. It's just a couple of steps, but I want to give you a feel for how this hydrolysis can occur. In the first step, the hydroxide ion undergoes a nucleophilic attack on a carbonyl group. Okay, that attaches the OH to the carbonyl carbon, and it converts the second bond on the carbonyl bond into a pair of non-bonding electrons on the oxygen. So that oxygen now has a negative charge in the product form there. I've drawn the bond in red to hydroxide to remind us that this is the new bond that was formed in this nucleophilic attack. In the second step, that extra pair of non-bonding electrons on that oxygen now comes back down to reform the double bond, so it reestablishes a carbonyl bond. But instead of kicking the OH off and just going back to what it used to be, it instead kicks off the RO group. It makes an alkoxide ion, and it forms the parent carboxylic acid. That is the parent carboxylic acid for the original ester. All right, so that ROH is now itself a very strong nucleophile. It's got 3 pairs of non-bonding electrons and a negative charge, so it can readily undergo a nucleophilic attack or even a base type proton transfer. And that's in fact what it does. That our alkoxide group can now abstract the hydrogen off of the carboxylic acid. Okay, the carboxylic acid has this acidic proton. RO negative is a strong base. So what ends up happening is it forms the alcohol, R'-OH, and it forms a carboxylate group, which once it adds a hydrogen from water or somewhere else, it too will be a carboxylic acid again, and we will have basically completed the hydrolysis part for the ester hydrolysis. So we can see that in this 3-step process, we've basically been able to use a base to get through all of the hurdles that an ester has in converting itself back to its parent carboxylic acid and its companion alcohol. But I want to point out that in this process, base is consumed by this reaction. So this is not a base catalyst, or base catalyzed process. It is a base promoted process. The base helps the process happen, but it also is consumed by it. Now, one last example of this is basically the process that we use to make soap. And this involves lye, which is also sodium hydroxide, reacting with a triglyceride. So this is basically an animal fat. This is how we might consume animal fat. And it helps promote that base-promoted hydrolysis. So when you have water around, what's going to end up happening is that the ester is hydrolyzed, it gives us back glycerol, and it forms 3 of these fatty acid salts. Now in this case, remember, we didn't get all the way back to the carboxylic acid. We formed an alkyl carboxylate, and in this case that carboxylate hooks up with the sodium ion that was accompanying the hydroxide in the original lye. So what it's making is not a carboxylic acid, but a fatty acid salt. And in this case, that fatty acid salt is what we call soap. And in fact, this will have the sort of cleansing properties that we normally associate with soap. Now, the soap that you buy in the store is a fancier version of this. This would be a pretty harsh soap, and you would probably not enjoy using it very much. But we found ways to tame its wilder and harsher aspects so that it's something that we don't mind using periodically and cleaning ourselves up. So I hope you've learned something about the distinction between stepwise and concerted reactions. And you've also picked up a little bit about the hydrolysis reaction and understand a little better about the important role that it plays in our biochemistry and even in the way that we make soap. Thank you.